Hello, I am Jonathan Trinh, and I am here to present my group and I's midterm project. So the project was a RISC-V dynamic tick scheduling where we were to implement an interval tick that is dynamic for the RISC-V. It is our midterm project for EECS211 operating systems at the University of California, Irvine. So as a quick introduction, here are all of the group members. There is Calder Staude, Jonathan Trinh, who is me, Justin Zhang, Tyler Zhang, and Yonatan Gizachew.
So for the next two slides, I'll give a brief overview of the changes that we made to the system. Here are the changes that we made to the scheduler, which will decide what interval to set the next tick. When the scheduler begins, the first thing that we do is update the metadata of both the system and the current process. One of the pieces of information that we use is the number of processes currently running on the system, the current number of runnable processes, that is, as well as the current process's yield count, or the number of times that the current process has given up control. And then when we calculate the yield count, we actually store that into the PCB. In the next step, the scheduler will pick a new process to run. And then because we stored information into the PCB about the yield count, we get that as another piece of information. And then the process yield count and the number of processes on the system both serve as metadata to feed our algorithm to decide what interval to choose next. In different algorithms, we actually have other pieces of information, such as the average yield count of processes running on the system. And we will be discussing the algorithms that we used in more detail on later slides. This slide describes the mechanics of exactly how we set the interval for the next tick, as well as how we read the system's time. So when the computer is running, a machine-level interrupt occurs every time the machine time register equals the mtime compare register. When that happens, an interrupt handler occurs called timervec, and in that handler, the mtime compare register is updated with the value of the interval. This interval value is tied to a machine register called mscratch. And what we actually found is that mscratch is exposed as a global array in start.c called timer scratch. This is where it's first allocated, and any updates to that value is actually reflected in the mscratch register. So when we want to update the interval value, all we need to do is update the corresponding value in the timer scratch array, and then the machine will read it in the next tick when it goes to update the mtime compare register. Since the interval between ticks is no longer constant, we thought it would be useful to have a method to determine the current time of the system for debugging purposes. So we made one change to the timervec handler. Now it also includes, it loads the value of the mtime register, and then stores it into timer scratch, so that whenever we need to read the current time of the system, all we need to do is load the corresponding value from the timer scratch array. And in that way, we can set both the interval of the system as well as read the actual time and cycles from the system.
So here we came up with three main approaches to solving this problem. Firstly, we have a three-tier system that increments the interval with, if you see a high yield count, it'll lead to a high interval, low yield count to a low interval. So a simple three-tier for that. Then we have a scaling-based approach. This works off of the yield count and does it more dynamically. And then lastly, we have a scaling based on process yield as well as state. So we look at how many processes are runnable and sleeping, as well as the yield count, and we average those to get a good interval, and we'll speak to those more shortly. So here's our three-tier interval settlings using a three-tier priority system. And as you can see here, we have a low yield count will correspond to a low interval, medium yield count to a medium, and a high to a high interval. The idea behind this is that if a process is trying to run and gets interrupted a lot, it'll make its way to a very high priority and then be able to run for a long time. And newer tasks that can maybe be done quickly have a low yield, low interval, and can just be operated on quickly and kind of get out of the way. So here you can see our flow chart for this. At the top we have our scheduler, and then that comes into our yield count, where we determine the yield count within our scheduler, and then based off this we set it to its associated level, being minimum, medium, and high, and then we go dynamically set our interval.
So the second strategy we employed was to determine the interval based on the relative yield count of a process to that of the average yield count, rather than merely utilizing a three-tier interval setting. And to determine the average yield count, first we sum up the yield count of the process in the CPU and divide it by the total number of processes. And the tick interval is here the interval is determined by the scale and the scale factor, and the scale factor is a constant value, and the scale is produced by subtracting the yield counts of a process from the average yield counts of all the processes, and we then later normalized it by the average yield count. So if the yield count of the processes is fewer than the average yield count, the scale will be negative, and as a result the tick interval for it to be reduced. But if the process yielding count exceeds the average yield count here, then the tick interval will be increased. We chose this method because we want to ensure that CPU time is distributed fairly among processes and no process will be starved. And one of the difficulties that we encountered when we implement this was we couldn't use floating point division. If we use it, the CPU panics, and using integer division is ineffective since it may result in undesirable approximation to a full number. Especially we had an issue when we calculate the scale, because in most situations the scale could be between 0 and 1 or 1 and 2, and during this time the integer division could be approximated to 0 and 1, but we don't want that result. And to circumvent this, we employed a certain method, such as multiplying some values by a constant number and dividing by the same constant number later. Like as you can see here, we multiplied this number by 10,000 and later we divided by 10,000. And this helped us to get the result. We were able to get an excellent result by doing so, and we also have another strategy in which we take the number of sleeping processes and running processes into account. In the next presenter, Calder will go through the code and we will see how different techniques perform afterwards using some graph.
So here you can see our approach for scaling based off yield count as well as state, and we have our scale factor, which we're applying to an average yield count, as well as the number of total processes running, as well as the total sleeping processes. And with all these factors, we are able to get an interval that'll dynamically adjust based off of the workload given to the processor. We'll provide a quick demo for you here now. So here we have our attempt 4. You can see our fairly involved method of changing our intervals. So this revolves around gathering heuristics about the general system with a total yield count, running count, as well as averaging performed on that. And that way these metrics stay relevant throughout the lifetime of the operating system running and don't get beaten out by hard-coded threshold values. We scale these to get our interval, and then we apply some logic into whether or not we have more or less sleeping processes. If we're seeing more processes sleep, then we'll increase our interval, as there's not high importance to make sure they are operating, they're not runnable. And if we're seeing a general decrease in sleepable processes, then we'll decrease our interval and speed up the whole system. To make sure that we have accurate heuristics throughout the program, we've taken great care to make sure that these values are consistent and accurate while running the process. So here you can see that we're increasing it on yield, and then also when a process dies, we remove that from the total yield count and keep consistent and accurate heuristics throughout the program. So here we're just going to run it quickly. So running this, you'll see we boot here, and we've created a user test cat to log the runtime of processes. So if we do a fork test, here you can see that duration, and you can see a variety of different things, such as user test operate and different items. But here you can see like echo, which is a quicker process run, and that performs like so. Thank you.
We collected execution finish time for the vanilla scheduler, the 3-tier interval, the yield count process state, and just the yield count. Given the 3 benchmarking tests, which are fork test, user test, and LS, we can see that in general, the dynamic schedules outperform the vanilla scheduler.
So, in conclusion, our algorithm of scaling based on process yield count and state did include the most features, and our algorithm of scaling based on yield count did prove to perform the best. Looking at the data, as mentioned previously, processes tested were shown to outperform the original vanilla processes. The brown boxes in the bar charts in the previous data slide were the original vanilla processes that were ran, with the other colors being our algorithms that we implemented.